Hi, this video will give a short description of a project called Isingler, which is submitted to Digital Design Contest. My project has such name because its goal is to implement the Ising model. This model is useful in physics where it can describe how magnets work. Hopefully this animation describes a little what is going on. What you see is a two-dimensional grid. Every point here describes spin state of one side in the grid. All the spins can have only two possible values, and these are represented by two colors. Every spin wants to be in the same position as its neighbors. This is the minimal energy configuration. But if our magnet is not cold, sometimes thermal energy comes and excites a spin to a state opposite to its neighbors. If the temperature is higher, this happens more and more. So in very warm magnets the configuration is very random. But at low temperature it is possible that the spins relax and stay in the same state as its neighbors. They form large blobs and the border of the blobs move around slowly. Sometimes the blobs merge. If the temperature comes very low, all the sides will have the same color. You can see how these blobs form at the lower temperatures, and at higher temperatures they will be completely mixed up. We can simulate this action on computer. For this we pick a random spin and ask if the energy decreases or increases if we would flip it to our state. If energy would decrease, we accept the change. If it would increase, we ask what is the temperature of the system. If the temperature is high, we accept the change with higher probability. The problem is that to make video you see, it takes a lot of time on a normal computer, as we have to play this flipping game for a long time before we see any blobs forming. But as Ising model is very interesting to scientists, we want a fast model so we could learn more about the physics inside. As each side only depends on the state of its neighbors, we can update many spins in parallel. As normal PC has only one processor, I programmed this model on FPGA where I am able to do many updates of spins in parallel. After seeing the animation, the physics of the Ising model does not sound so complicated, and it is not. The first equation you see is called the Hamiltonian. This gives the energy of a system, but non-physicists don't need to read it. Without going into details, the long equation in the center is the translation of this Hamiltonian for programmers. It states that energy one spin has is given by just XORing the spin states with all its neighbors and adding it together. And then you have the formula for spin flip probability as a function of energy change on spin flip. This really is not complicated and is enough to understand the program. The complicated physics comes into play when you want to understand why this algorithm is correct or what to do with the data you get from it. Now you see a simplified description of the structure of a Verilog code I wrote to simulate the Ising model. In the center there is an Ising core. It has 15-state final state machine which directs the data flow. The core is connected to DRAM memory where the data is stored, and it also controls the 64 Ising cells, which are modules which actually flip the spins. Both the core and cell need some random numbers. Using the input and output ports, it is possible to set parameters, read statistics and control the final state machine. But when looking at the details it is a bit more complicated. There is a middleman in communication between Ising core and PC. I used another small software processor called PicoBlaze provided by Exelinks. These plots describe how they are connected and what is inside the Ising core. If you are interested in it, please check the report I have attached to the video. To find many spins from memory in parallel you need some sort of smart data structure. Mine looks like checkerboard. For this to work you need to figure out how many colors you use for a given three-dimensional checkerboard such that no neighbors would have the same color. You also need few tricks to find the data from the color you need from the memory. This algorithm also needs a large amount of random numbers. In this project 66 bytes of good quality pseudo-random numbers are produced at 100 MHz using linear feedback shift registers made from shift register primitives. And best of all, it works. I am showing you the demonstration program. It is called simple control. I just call it with two parameters. The port ID where my FPGA is connected and the number which is the temperature of the Ising model I want to simulate. The program sends the configuration and Isingler starts processing. The processing is really fast, but I let it do 100 million spin flips on 44 times 44 times 44 read, so you could see that something is going on. And then it starts downloading the data from the Isingler's memory, just to show you that there is something actually connected to the computer. This is Atlas board with FPGA Spartan 6. And the output of the demo program is 44 images of every layer from the cube. I thank you for your interest. If you would like some more information, please feel free to contact me or check out the report I have attached to the video. Live long and prosper.